Grid-connected and islanding operations. Grid-connected and islanding operations are concepts related to electrical power systems and the operation of distributed energy resources, DERs, like solar panels, wind turbines, and energy storage systems. Let's explore each term separately. Grid-connected operations. Grid-connected operations refer to the standard mode of operation for most power generation systems and consumers. In a grid-connected setup, power generation sources, such as power plants or renewable energy sources like solar and wind, are connected to an interconnected network of power transmission and distribution lines called the electrical grid. Consumers, such as homes, businesses, and industries, are also connected to this grid. Key characteristics of grid-connected operations. Bidirectional power flow. Power can flow in both directions, from the generation sources to the consumers and vice versa. Power plants supply electricity to the grid, and consumers draw electricity from the grid as per the demand. Stable frequency and voltage. In a well-maintained grid, the frequency and voltage levels are regulated within specific tolerances to ensure the reliable and efficient operation of electrical devices. Centralized control. Grid-connected power systems are centrally controlled and managed by grid operators who monitor and balance the electricity generation and demand to maintain grid stability. Interconnection of multiple sources. Various power generation sources can be interconnected, including fossil fuel power plants, hydroelectric plants, solar farms, wind farms, and more. Islanding operations. Island mode or islanded grid. Islanding operations, also known as island mode or an islanded grid, occur when a portion of the electrical system continues to operate in isolation from the main grid due to a grid disturbance or a fault in the main grid. This typically happens when there is a sudden loss of grid connectivity due to a fault, maintenance, or a natural disaster, and certain localized areas still have power generation sources available. Characteristics of islanding operations. Isolated power supply. The isolated portion of the electrical system operates as an independent microgrid, relying on local power generation sources and energy storage systems to meet the electricity demand within that area. Limited power resources. In islanding mode, the available power generation sources are limited to what is present within the isolated area.
Nonlinear controllers. Nonlinear controllers are designed based on nonlinear control theory, which allows for more complex relationships between the input and output. These controllers are employed in systems with highly nonlinear behavior or when the operating range extends beyond the capabilities of linear controllers. Nonlinear controllers often use advanced control techniques, such as adaptive control, fuzzy logic control, or model predictive control, MPC. These techniques can handle more complex and dynamic systems and may provide better performance in certain scenarios. A fuzzy logic controller, FLC. Fuzzy logic controllers use linguistic variables to represent the system's behavior. Instead of using precise mathematical models, FLC relies on human-like reasoning to make control decisions based on fuzzy rules. It is particularly useful when dealing with uncertain or imprecise information. B. Model predictive control, MPC. MPC uses a dynamic model of the system to predict its behavior over a future time horizon. It then optimizes a control sequence to achieve desired objectives, such as maximizing energy production or minimizing costs. MPC is effective in handling constraints and disturbances in renewable energy systems. C. Adaptive control. Adaptive control techniques adjust controller parameters in real time based on the system's changing characteristics. This approach is suitable for systems with uncertain or time-varying dynamics. In renewable energy generation systems, nonlinear controllers are often employed in complex and dynamic components like grid-tied inverters or energy storage systems, where the behavior is nonlinear and requires sophisticated control strategies. In summary, both linear and nonlinear controllers play essential roles in renewable energy generation systems. Linear controllers are commonly used in simple systems with relatively predictable behavior, while nonlinear controllers are employed in more complex systems that require advanced control techniques to achieve optimal performance. The choice of controller depends on the specific characteristics and requirements of the renewable energy system being controlled.
Filters for grid-connected system. In the context of a grid-connected system, filters play an essential role in ensuring the efficient and safe operation of the system. Grid-connected systems, like solar power systems or wind power systems, are designed to feed electricity into the utility grid. These systems generate electricity from renewable energy sources and synchronize their output with the utility grid's voltage and frequency. Here are some common types of filters used in grid-connected systems. Harmonic filters. Harmonics are undesirable voltage and current distortions that can occur in grid-connected systems due to nonlinear loads or power electronic converters. Harmonic filters are used to mitigate these harmonics and ensure the system's compliance with grid codes and standards. They can be passive, e.g., inductors and capacitors, or active, e.g., using power electronic devices to actively cancel out harmonics. ME, electromagnetic interference, filters. ME filters are used to suppress electromagnetic interference caused by the switching of power electronic devices in the grid-connected system. They prevent the system's high-frequency noise from affecting other sensitive electronic equipment on the grid or nearby. Power quality filters. Power quality filters are designed to address various power quality issues such as voltage sags, voltage swells, voltage flicker, and other disturbances. These filters help maintain stable and high-quality power output from the grid-connected system. Low-pass filters. In certain applications, a low-pass filter may be used to smooth out rapid voltage or current fluctuations and prevent high-frequency components from reaching the grid. High-pass filters. High-pass filters can be used to filter out low-frequency components in the system's output. They are used in specific cases where low-frequency content may need to be removed before the electricity is fed into the grid. Notch filters. Notch filters are used to attenuate specific frequencies or frequency ranges. They are employed when there are known frequency components or interference that need to be eliminated from the system's output. Anti-islanding filters. These filters are a critical safety feature for grid-connected systems. They detect islanding situations when the grid goes down, but the renewable system continues to generate power, and they disconnect the system from the grid to prevent feeding power into a potentially damaged grid.
Islanding detection methods. Islanding detection methods are techniques used in electrical power systems to identify and detect instances when distributed energy resources, DERs, such as solar photovoltaic systems or wind turbines, continue to generate power in an isolated manner during a grid outage. When a power outage occurs, the main grid shuts down to protect utility workers and equipment. However, if a DER system is still generating power during this time, it can create a potentially dangerous island of energy that could cause harm to workers attempting to repair the grid. Detecting the occurrence of islanding is crucial to ensure the safety and stability of the overall power system. Here are some common islanding detection methods. Frequency-based methods. These methods monitor the frequency of the electrical signal in the system. During normal grid-connected operation, the frequency remains relatively stable. However, when an islanding event occurs, the frequency may start to deviate from the standard value. Frequency-based methods include rate of change of frequency, ROCOF, and under/over frequency relays. Voltage-based methods. Similar to frequency-based methods, voltage-based methods monitor the voltage levels in the system. A significant change in voltage could indicate an islanding condition. Voltage-based methods include rate of change of voltage, ROCOF, and under/over voltage relays. Impedance-based methods. These methods analyze changes in the impedance characteristics of the power system. During an islanding event, the impedance may differ from the usual grid-connected values. Techniques like positive feedback impedance and reactive power voltage relays fall under this category. Rate of change of power, ROCP. This method measures the rate at which active power, real power, changes in the system. A rapid change in active power may indicate islanding. Frequency watt, FW, or voltage watt, VW, control. Some grid-tied inverters in solar photovoltaic systems utilize FW or VW control algorithms to detect islanding. These methods monitor the grid frequency or voltage and adjust the inverter's power output accordingly. If the grid parameters deviate beyond certain thresholds, the inverter may disconnect from the grid to prevent islanding. Communication-based methods. In certain cases, communication between DERs and the utility control center can be used to detect islanding.